basically you have to calculate the reactions. So we have two uh, cylinders with shafts. So this is the first one, and this is the second one. So there are three questions. The first question is you have to like figure out if this is a determinate system or an indeterminate system. So that's the first part, and then you have to calculate the reaction loads. And this example is exactly what we were talking about in the last lecture. So this is exactly the same. So you have to calculate the reaction loads. First, you have to figure out is it a determinate system or not, and then you have to calculate the reaction loads, and then you have to figure out which of the reaction load is actually a torque. So these are the three questions. And if you don't know if it's a determinate system or indeterminate system, so you can try to calculate the reaction loads. If you can figure out the reaction loads, then the system is determinate. If you cannot figure out the reaction loads, then the system must be indeterminate. So these are the three questions. And when you are like done doing the uh, problem, you can make a box, and I will grade you based on the box. Like you can make a box, you can put if it's a determinate or indeterminate. For let's just say this is a determinate system. If this is a determinate system, you will put determinate here, and let's just talk about this. You will have Rx, you will have Ry, you will have Rz, you will have moment along X, you will have moment along Y, you will have moment along Z, and give me values in Newton, and this should be Newton meter. So you have to calculate these values, and here you can say torque, and you can put a value of torque. I mean, one of these moments, or two or three, some of these moments is actually a torque. And you can take this value out and put it here so that you will know which of the moment is actually a torque. So the question was, is the system determinate or indeterminate? So if we can solve for this and we can calculate the reaction, then the system is determinate. If we cannot calculate the reaction, then the system is not determinate. So uh, these are the six equilibrium equations which we're going to use, and we're going to see how, yes. Uh, you mean these forces? What's your question? But it doesn't matter. Even if you have reversed, you can answer should be but I've tried to make it like exactly the same. But even if you flip it, you're gonna end up like negative, but your answer will still be correct. So if you do summation of forces along x-axis is equal to 0, how many forces are there along x-axis? I cannot see any force other than Rx. So Rx is equal to 0. If you do summation of force along y-axis is equal to 0, this is the force, reaction force, which is acting along y-axis, R of y. This is the force which is acting along y-axis, negative 800 because it's downward. This is the force which is acting along y-axis, so it's positive 1200 Newton is equal to 0. So you will end up getting Ry is equal to, if you do, that's going to be negative 400 Newton. So that's the answer for reaction Y. If you do summation of forces along z-axis is equal to 0, so this is the force which is acting along z-axis, and there is no other force. This force is along y-axis, this force is along y-axis, so it's gonna be Rz is equal to 0. If you do summation of moment along x-axis, so this t of x, for t of x you can put m of x, like, so this t of x is actually, let's put m of x. This is the moment along x-axis, right? So if you do summation of moment along x-axis is equal to 0, you're gonna get m of x. Let's just say this is positive, and then this force is also gonna create a moment along x-axis. So that's the moment, right? So the thumb, if the thumb is pointing along x direction, then you can know that this moment is actually acting along the x-axis. So if you try to imagine the rotation, if you try to draw this moment, your thumb is gonna point along x-axis. So this is, we have to consider this. If you see this force, and if you try to see how this force is creating a moment, so this is also creating moment, something like that. So your thumb is pointing along x-axis, so we have to consider this force. So force is 800, and the moment arm is 40, which is the diameter, divided by 2 because it's the half. And then I will multiply by 100 because I have to convert centimeter into meter. So, so if you draw a moment, you're going to get your thumb pointing towards the x-axis, and that's how you can know that this is a moment we have to consider when we are talking about x-axis. But you also have to think about like the moment arm. So in this case, the force is going to twist the system in along x-axis. So that's the moment arm. So the moment arm is 40 by 2. And then for this force, it's going to be negative because the thumb will point opposite to the axis we have considered positive. So you're going to be 1200. Yes. Yeah, I mean, when I draw this way, because last time also I've realized, when I draw this way, some of guys will think it's in this direction, some of guys will think in this direction. It's just how you draw. Like, I think how many of you guys think it's it should be positive? How many you think it should be negative? So it's just an illusion, you know. But so I cannot draw it this way. But if you think it's negative, you can put negative. Yeah. Yes. Yeah. Yes, yes, you should, you should. And I'm actually like, this is just like 3D. This is first example, but otherwise I will give you another way because instead of drawing this way, we should like draw double arrow. Then we're not gonna make a mistake. But for sure we should be consistent. But this is a simpler example. That's why we're gonna get the right answer anyway. But otherwise, yes, uh, whatever we have assumed in a free body diagram, we should stay consistent. Yes, yes, absolutely. So this is gonna be 30 by 2 into 100 is equal to 0. So you're gonna end up getting moment as 20 Newton meters. Some of you will get minus 20, some of you will get positive. Both are correct because of this, like, you know, we have drawn it in such a way. But if you got 20, that's correct. If you do summation of moment along y-axis is equal to 0, so m of y should be equal to 0. If someone thinks it shouldn't be 0, we can like talk about it, but I think like moment along y-axis is equal to 0. If you do summation of moment along z-axis is equal to 0, then let me draw this in a 2D way. So if you draw a two-dimensional, you will get this force which is 800, this force which is 1200, and you have a moment which is m of z. If you, this is a 3D, but if you just look at from one axis, you try to make a 2D, this is how it looks like. So from here also, if you do summation of moment is equal to 0, you'll get m of z negative 800 into this distance, which is 10. So it would be 10 divided by 100 plus 1200 into 10 plus 8 divided by 100, which is, this is 8, right? This is 10. So that's the moment arm for 1200 is equal to 0. So moment at z would be equal to minus 136 Newton meter. So you have three moments, and this moment m of z is not going to create torsion, it's going to create bending. You can see if you try to draw how it's going to bend, it's going to bend something like this, you know. I mean, this force is pushing this beam down, this force is pushing the beam up. So this is not torsion actually. This phenomena is called bending. So bending moments produce bending. But if you try to see this moment, m of x, so m of x is actually twisting the member, twisting the system. It's not creating bending, it's creating twisting. So the answer is this one. This is actually torque. 20 Newton meter is torque. 136 Newton meter is not torque. So if you want to draw the answer, it should be, it's a determinate system because we were able to calculate all the reaction loads we needed. So it's a determinate system. Rx is equal to 0, Ry is equal to negative 400, Rz is equal to 0. Moment along x-axis was 20 Newton meter. Moment along y-axis was 0. Moment along z-axis was negative 136 Newton meter. And whoever has got these values, then he have done it right. And this moment is actually a moment because it's creating bending. This moment m of x is actually torsion. This is not moment, this is torsion. So A was determinant system, B was calculating the reactions, and C was figuring out which of those moments is actually a torsion. So I hope it's clear. Is okay? All right. So this is what we were talking about last time. So we know what torque is, and we know because of the torque we'll have torsion, and because of the torsion we'll have angle of twist, and we will have shear stresses and shear strains, and this is how we can calculate angle of twist. So this is the formula for angle of twist, which is TL over GJ, and G is actually shear modulus of elasticity. And if you know Young's modulus of elasticity and Poisson ratio, you can calculate the shear modulus of elasticity. And J is a polar moment of inertia, which is a geometric property of a circle shape. So if you know the radius, if you know the diameter, you can calculate the polar moment of inertia. So maybe you can write it down, these equations, but in the exam, I will give you the equations as well and give you the values of modulus of elasticity or shear modulus of elasticity, one of them. So you don't have to remember, but these are like 3-4 equations, and it's good you can write it down. So this is for the angle of twist. How much rotation you're getting at the end, you can calculate by using this equation. And also these are the equations because torque is producing shear stresses and shear strain. So these are the equations for shear stresses and shear strain. In the workbook, maybe the notation would be a little different, and also they have explained how you have ended up in these equations, but these equations is all you have to remember and figure out from these equations how you can calculate shear stresses and shear strains. So basically you have 3 equations: angle of twist, and you have shear stresses and shear strains, for which you need polar moment of inertia and shear modulus of elasticity. So let's continue doing our example. So this, we have already calculated the reactions. The question is, in this example which we were doing, the first part was calculate the torques. We have already calculated the torque and the reaction loads. We have calculated. The second part for this example is to calculate angle of twist. So now we have to calculate angle of twist. Phi A and phi B. This is the second part of this example. So now we're going to calculate angle of twist, and the formula for angle of twist is TL over GJ. So this is the formula for the angle of twist. So we have to figure out what's length, what's G, what's J, what's the value of torque, and if we know all these values, we can calculate the angle of twist. But we have to calculate angle of twist at this location, phi A, and we also have to calculate angle of twist at this location, which is phi B. So this is member 1. We know this was made up of brass, I guess. This was made up of brass. This was made up of aluminium. So the modulus of elasticity for the brass was 100 gigapascals. Poisson ratio was 0.34. The modulus of elasticity for aluminium was 70 gigapascals, and the Poisson ratio was 0.33. So if we know these values, we can calculate G. If we know the diameter, we can calculate J. We already know the length. This length is 10 centimeter. This length is 8 centimeter. So we can calculate the angle of twist. But if you imagine, if you try to visualize how this twisting is gonna be, so this is the straight line, right? This is the straight line, but it will try to twist, and the straight line will go somewhere here after the twisting, right? So from here we can calculate the angle of twist at this location. But this shaft B, is trying to twist the member in other direction. So from here, the twisting is going to reverse. And here also we have to calculate the angle of twist. So you can imagine how the twisting is happening. So this is a fixed support. This is a fixed support. So here there is no twisting. Like it's like the angle of twist is 0 here because no twisting. But if you go to the shaft A is twisting the system in this direction. So you're gonna get a line down. And then the shaft B is twisting on the other direction. So that's how you can imagine how the twisting of a system is happening. But anyways, let's try to figure out the angle of twist for A. So if you want to calculate the angle of twist for A, you need a torque T1, you need the length L1, you need G1, J1. So if we know T1, L1, J1, G1, we can calculate the angle of twist. So let's just try to find these values. Yeah, so L1, we know what is L1. L1 is 10 centimeter, which is 0.1 meter. What is L2? L2 is 8 centimeter, which is 0.08 meter. Now let's try to find G1. So the formula for G1 is E by 2 1 plus phi. And the formula for J1 is pi by 2 R4. So we can find G1 and G2 and J1 and J2 and L1 and L2 and the torque T1, T2, and then we can calculate the angle of twist. So the value of G1 would be E1 over 2 into 1 plus Poisson ratio 1. E1 is 100 gigapascals and 1 plus 0.34. G2 is E2 by 2 into 1 plus Poisson ratio. So this is 70 gigapascals over 2 into 1 plus 0.33. So you're going to get the G1 value as 37.3 gigapascals, and you will get the G2 value as 26.3 gigapascals. We can also calculate J1, which is pi by 2 R 4, and it's J1, so we should use R1. Pi by 2. What is R1 in this case? It is D1 by 2. Because we have given so many diameters. The diameter D1 is 1 centimeter. The diameter DA is 40 centimeter. This is D2, which is 1.5 centimeter, and this is DB, which is 30 centimeter. So you need to think about it like which is the D1. There are 4 diameters given. So pi by 2 into, I would say this is 1 centimeter. 1 centimeter, so divided by 100 to make it meter. So if you think the diameter should be something else, you can let me know. So J1 would be equal to 9.817 into 10 raised to the power minus 10 meter 4, because it's like radius power 4, so you're going to get meter power 4. And for the J2, you're going to get pi by 2 R2 power 4, pi by 2 D2 by 2 power 4, pi by 2. And the value of D2 is 1.5. I'm going to divide by 100 to make it meter. So the value of J2 would be equal to 4.97 into 10 raised to the power minus 9 meter 4. So we have G1, we have G2, we have J1, we have J2. So we have G, we have J, we know the length. All we need to know is what is the value of torque. So if we know torque, we can input the values, we can calculate the angle of twist. And we have already calculated reaction loads for this. We already know what is the reaction torque. But this torque is actually an internal torque. Like in chapter 3, when we were calculating the stresses and strains, we were using internal reaction loads. So that's the one which is going to create stresses and strains. In this case also, torque is actually an internal torque, because internal torque is responsible for the angle of twist. Internal torque is responsible for the shear stresses and the shear strains. So the torque you have calculated in the quiz is actually a reaction load. We have to calculate internal torques. And how we can calculate internal torque is by determining free body diagrams and cutting the sections. So this is what we're gonna do next time, but I'm gonna give you guys a hint. So we have torque here, we have torque here, and this is the reaction torque you guys have calculated, right? This was 20 Newton meter torque. So we're gonna cut a section next time, and we're gonna expose internal torques, and that's the internal torque which is gonna go into this equation.